title is Logarithmic Prismatic Site.
Okay, thanks for introduction and the invitation. So it's my great pleasure and honor to give a talk on this occasion. Takeshi Sensei was my teacher in my undergrad, and I mean, he has been influential, and I had many chances to talk to him, and also because my PhD advisor was Gato, and Kato and Saito are good friends. And yeah, so as Bhatt explained, so Frobenius-Witt differentials seems to be related to prismatic stuff. And also, Takeshi Sensei is a master of log geometry. So yeah, I'm happy to talk about log prismatic theory today. Okay, so let me start. So the title of this talk is Logarithmic Prismatic Site. So unlike Bhatt, I use the classical site theoretic approach. The first paper is available on arXiv. Well, and I guess most of the materials from today's talk can be found there. Not all though. And I'm also preparing a sequel with Zhen Yao, but I guess I will not say much about this part, actually. Okay, so let me first explain one motivation. So fixed prime P, oh, sorry. And let K be a finite extension of QP. And let OK denote ring of integers, little K residue field. And take a uniformizer. Then we obtain a surjection. So this is basically Berger explained the purification prism. So we have a surjection sending U to pi. Kernel is generated by Eisenstein polynomial. Okay. And now let X be a semi-stable scheme or formal scheme. Over K. Then, so it has been expected to, yeah, I mean, the following cohomology was expected. So, so-called Brooksian cohomology. So this should be a, oh, let me assume X is proper for simplicity. Then this cohomology should be a perfect complex of modules of this ring WKU. And equipped with Frobenius structure, satisfying certain condition. And also this should be a descent of so-called A-inf cohomology. So this was constructed by Bhatt and Scholze in the smooth case, and the semi-stable case was worked out by myself and Tesson-Vicious. yeah. So one goal is to construct this cohomology for semi-stable schemes or formal schemes. Okay. And for X smooth, Bernoulli cohomology was first constructed. I mean, this was already solved and first constructed by Bhatt and Scholze using topological homology or its variant. And later, Bhatt and Scholze reconstructed Bernoulli cohomology as a special case of prismatic cohomology. And so we try to use this second approach to attack the semi-stable case. And because so any semi-stable scheme over OK is log smooth in the framework of log geometry. I mean, it's natural to guess like Bernoulli cohomology in the semi-stable case is also a special case of log prismatic cohomology. Okay. And indeed, I mean, as Berger discussed, prismatic cohomology is a kind of refinement of a generalization of crystalline cohomology. And crystalline cohomology was generalized to log crystalline cohomology by Kato sensei. And I mean, this is what Kato sensei did in his first paper on log geometry. So I think this suggests like this log geometry approach is promising. Okay. And so, yeah, I'm going to explain how this works, actually. Okay. All right. So, yeah, I mean, Takeshi sensei knows log geometry very well, but I want to explain log geometry for general audience. Okay. So, a review. So let X be a scheme or a formal scheme. Okay, and then a prelog structure is the following. So it's a map of shapes. So here MX is a tau sheaf of monoids, or more precisely commutative monoids. And OX is regarded as, OX is regarded as a monoid with multiplication. And this is a log structure. If the inverse image of OX times is isomorphic to OX times. Okay, yeah, this is just a definition. And so, yeah, so I mean, log scheme, or maybe prelog scheme, or prelog homo scheme, etc., is X plus log structure. Okay. One can also define. So can define prelog links or log links. Well, I mean, these already appeared in previous talks, but yeah, let's make them a bit. So, so this means you have a ring and commutative monoid and a map between them. And this is log if this map satisfies a similar condition like this. Okay. And so scheme is locally modeled by a ring, I mean the spectrum of a ring. And like schemes, log schemes or parallel schemes are locally modeled by log links or log rings. Or more precisely, in practice, we only consider such log schemes. But anyway, I mean, often locally we only consider like rings with monoids. Okay. So examples. So let X semi-stable over K. So this means X is entirely locally entirely over the following ring. Yeah, because I'm explaining the case of schemes. And if you are working with formal schemes, then you should complete it. Okay. For some S, sorry, some R and D. Okay. So in this situation, so at least entirely locally, you can consider the following map. So here n is natural numbers regarded as an additive monoid. And I mean, this identified with the following monoids. Yeah, and you have natural map. So this is an example of prelog structure. And a basic idea here is, so given such a prelog structure, we want to consider associated log differentials. Namely, we want to consider log differentials like the x naught over x naught, the x1 of the x1 of x1, da da da.
Sorry, if you start from 0, then there must be R plus 1 factor.
Yeah, I mean, there is a relation. I mean,
Yeah, but you write the monoid, monoid in R.
Ah, sorry. Oh, okay, here.
Yeah,
Okay.
yeah. Mm.
Sure. Yeah.
Sorry. Yes.
Thank you.
Hmm.
Yeah. So back to here. So we want to consider such log differentials, and this satisfies a simple relation. And I mean, without denominators, I mean, you can still consider usual differential, but it satisfies some complicated relation. But by considering this kind of log differentials, relation becomes simpler, and this is good for like consideration of Dirac homology or eventually like prismatic homology, etc. Yeah. Okay. Yeah. So this is an example of prelog structure, but this one is not canonical. I mean, depending on a choice of coordinates. But there is a more natural one you can consider. So the not canonical one is the line. Consider intersection. I mean, section that becomes invertible after inverting P. Okay. Like T naught, T1, T out, this becomes invertible. I mean, if you invert pi, right? So, I mean, this is bigger than this model, and this is an example of log structure rather than prelog structure. So, yeah, to have something canonical, we need to work with log structure. Okay. Yeah. And with these log structures, X is smooth over OK. I mean, OK has a canonical log structure in this way. So that is monoid is given by non-zero elements. Yeah. What else should I say? Oh, by the way, like this kind of situation, I mean, locally you have a map from constant monoid, but you also have a like natural log structure. Then we call such a map from constant monoid is a chart. Yeah, this is just a terminology. Okay. Yeah, one more example. So let's consider WKU as in the Brooke-Kishin set law. Then one parallel structure I can consider is a map from puzzle U. Or add all the units. And this is a kind of lifting of OK, namely, we had a suggestion to OK, sending U to pi. So yeah, again, I mean, these rifts are okay. I mean, this one. So yeah, I mean, somehow I'm trying to take the homology of X symbols over OK using this rift. Okay. Okay. So this is a review of log geometry. And before going to log prismatic theory, I guess I should say something about prismatic theory itself. And well, Bhatt have already explained something, but here's also some explanation. Yeah, so let me just explain the definition of the absolute prismatic site. So here X is a p-adic formal scheme, any, and so this is an absolute prismatic site. So this is a category of diagrams of the following form. And here AI is a bounded prism. Oh. and that means I ignore the technical boundedness condition, but A is a p-adically complete ring or delta ring. So namely, there is a self-map A to A and satisfying the following condition. Well, if you've never seen this relation, maybe you feel this is complicated, but this is just made so that the following map, so phi, x to the p plus p times delta, yeah. So this condition implies that this map is a ring endomorphism. And so namely, this is a Frobenius rift. Yeah, so this is the notion of delta ring. And I is an invertible ideal satisfying some condition. Yeah, but yeah, this is just definition of bounded prism, or say prism. Boundedness was a technical condition I ignore. Yeah, and you have a map from this closed subscheme or former subscheme to X. Right. So yeah, I want to consider some logarithmic version of this site. Okay. And then, I mean, we first need to generalize this notion of delta ring. Okay. And that's what I call delta log rings. Okay. So this is the analog of delta structure in the log setup. So definition. Let A M be a parallel ring. And A is a delta ring. Then we consider map from M to A. Okay. So this is a data log structure. So data log structure is a map of this form satisfying the following condition. So I need to write a condition like before. So data log of 1, unit is 0, and data log should be compatible with this data, given data. And so the condition is m to the p times data log of alpha of m is equal to data log of m. Okay. Is equal to delta of alpha over m. And finally, data log should satisfy something about multiplication. So data log of m times m prime is equal to data log m m plus data log m prime plus p times data log. Yeah, there was a this condition, and basically we just divide by powers to obtain this condition. Okay, and this, by the way, this implies a 1 plus p data log is multiplicative on m. Yeah, this is a definition of data log ring. Data log ring is this given data plus data log structure. Okay. Yeah, so I want to make some remarks. So the first thing is, I guess, Frobenius rift. I need return mode assumptions. So assume A is, say, p-adically complete. And also, in this definition, I allow all parallel rings. But here, I assume AM is a log ring. Okay. Now this element 1 plus p times data log is a unit. Because A is p-adically complete. And because AM is a log ring, we can regard this element as an element of M. So I define a self-mark of M by applying phi of M is equal to m to the p times 1 plus p times the log m. Okay. And as I said, 1 plus p times delta log is multiplicative. So this is an endomorphism of monoids. And this with the Frobenius rift of A, namely, there's a commutative diagram. Yeah, this is commutative. Yeah, so this thing is nice, right? I mean, okay. Okay, so next I want to mention some examples. Okay, so the first example is the trivial log structure. So this is a trivial log structure given by units. And assume A is a delta ring. Then delta log of A, I mean, here is a unit, must be delta over A divided by HB. And this is indeed a delta log ring. Okay. So another example is a Grisham one, so namely consider WKU with monoids U by powers of U. And yeah, as Berger explained, so data log structure here is the one delta U we call 0, namely phi U is just U, is power of U. And this means if we take data log of U to be just 0, then this becomes a data log ring. But as I said, I mean, this is just a pre-log ring and not the log ring. And so, I mean, to have something canonical, we should consider log structure. And so here we should consider something like powers of U times units. But you can, you know, I mean, you know what it should be, right? Okay. Okay, one more thing I want to explain is a following lemma. By the way, any questions so far? No? Okay. So useful lemma. Oh, maybe another thing I should say is, so the category of data links has very nice formal properties. And yeah, but I mean, Berger explained like adjoint function exists like that. And also limits exist, co-limit exists like that. Okay, so and like category of data links, the category of data log links also satisfies very formal, I mean, nice formal properties. Okay, but yeah, but I skip that. Okay. So next I'll explain useful lemma. This is slightly technical, but it's very important later. So assume AM is a data log ring. Say A is p-adically complete. And M is integral. And that means M injects into the associate group. For any, commutative monoid, you have the associate abelian group. And this condition integral means that the natural map is injected. Okay. And now take a submonoid inside this group containing M. Okay. So yeah, so these are assumptions, and the conclusion is the following. So in this situation, the following pair so the monoid part is now given by N, version 1. And to have a map from N, we extend the ring bit. So by the way, if AM is a prelog ring, you have a natural map from the M to A. And we use this natural map to get, to take this tensor product. Okay. And also you can replace this by suitable completion. Okay. And the claim is this is a data log ring. So in particular, this ring, this tensor product, is a data ring. Data structure extends. Okay. So this is important, because so later we need to use so-called exactification. And for exactification, we need this kind of operation. Like we need to extend, and we need to replace M by a larger monoid inside the same group. Okay. And I guess the last claim fails, without existence of data log structure. So this the data log structure helps to find data structure. Okay. Yeah. Now, let me define the site. Okay. The log prismatic site. Let X and X be a log p-adic Homer scheme. And for simplicity, say this is a fine log scheme. So this is locally admitted chat given by a finitely generated integral monoid. It's a kind of technical condition in log geometry. Okay. Then the absolute site is the following. So we write mx, please. So object here is like following diagram. So here, I should explain several things. So AI is a bounded prism. And AMA is a data log ring. And also, to make it natural, I assume MA is isomorphic to the global section of the log structure. Associated with MA. Okay, this is a kind of log applying condition. Okay, and also I guess I also assume MA is integral. And morphism here means so you have this p-adic Homer scheme of L by I, and with a map from MA, and we consider the associate p-adic Homer log scheme, log p-adic Homer scheme, and this is a morphism of log p-adic Homer scheme. So as log p-adic Homer schemes. Yeah. Okay. Yeah. So this is a object, and the morphisms are obvious ones. And the topology, well, I guess I forgot to explain topology in the non-log case, but anyway, the topology is topology. Well, there are choices, but say strict web topology. I mean, strict means like log structures are preserved. And yeah, I mean, this is just a condition on underlying scheme. Okay. Yeah, this is a definition of the site. Questions? All right. Okay, so let me mention some example. consider, oops. Wait a minute. Okay, I continue. Say X is okay with the canonical log structure. Then in this absolute side, we have the following object given by purification stuff. So WKU, Eisenstein polynomial, and the log structure I explained before. And actually, the following holds them. This object is weakly final. I mean, any object admits a map to this object up to, I mean, with respect to flat topology. Or, I mean, in other words, the sheaf represented by this object is a covering of the final object of the topos. So you can use this object to study this absolute side. Okay. And so I was planning to explain a little bit more about this example, but okay, maybe so. Product exists. And I mean, we should compute product of this object. And so let me explain how it looks like. So yeah, so I guess it is easier to think about non-log case first. So non-log case. Then the product of two copies of this object is like the following. So WKU, oops. And now we consider two variables. And to make it a prism, we need to apply some operation. And that is the following. So we consider difference. I mean, there's a natural map to OK, but U0, U0, and U1 both map to pi. And so we somehow modify the kernel. So somehow we add this element inside the category of data links. And also, I guess we should take some we should take some completion. Okay. So next, the log case. So here, we need to apply the exactification process I mentioned. And the output is the following. So WK, U0, U1. But now we consider quotients like this. And because, I mean, now at the level of monoids, U0 and U1 again are mapped to the same element. And in such a situation, we should add this kind of difference. Okay? And then we apply the same kind of operation. Okay, so namely, we take the prismatic envelope. Yeah, basically, this is called prismatic envelope. And again, maybe some completion of it. So the lemma I mentioned is useful in this process. Well, actually, in this process, the lemma is almost trivial, I guess. But in general, I mean, data log structure is more complicated and the lemma is helpful. Okay. So let me mention one result. And this is not my own result. This is a result of Hendu and Tonliu. But what I will state is not, I mean, you cannot find the statement in their paper, I mean, their current preprint, I guess. So this is a version of the statement. Using the lemma I mentioned, I mean, this object is weakly initial. Okay. So the theorem is the following. So the category of F crystals on this absolute site is equivalent to the category of latticing semi-stable Galois representations. So in the non-log case, this result is due to Bhatt Scholze. I mean, they prove a version of this statement replacing semi-stable by crystalline. And my understanding is Hendu and Tonliu find a different proof of this result of Bhatt Scholze that works in the log setting as well. Okay. So yeah. Okay. Finally, let me explain a bit about cohomology. So this is a relative one. I mean, I don't know anything about absolute prismatic cohomology. Fix AIMA. Oh, say log prism. I mean, this is the object of the. Well, I mean, I guess I didn't define log prism, but this is like one appearing in the definition of the site. I mean, yeah, I mean, I call this kind. Yeah, I call this kind of data log prism. Okay. So fixed log prism. And let x mx is a p-adic log p-adic Hummel scheme over a over I ma. And assume this map is smooth, or I mean log smooth. Everything is in the framework of log geometry. Okay. And integral and of Cartier type, or maybe I should say the multiple fiber is of Cartier type. So these are technical conditions in log geometry. So please ignore if you don't know them. Okay. Then, oh, well, I guess I don't have much time. So last theorem is so this is a relative side. I mean, everything lives over this log prism. Yeah. Okay. The cohomology of the structure shear satisfies. I mean, well, satisfies expected properties. Such as crystalline comparison, Hodge state comparison, or drum comparison, etc. So in particular, we obtain Brillouin cohomology by applying this theorem to the Brillouin setting. I mean, semi-stable schemes of OK. Yeah. All right. Maybe few words about proofs. So the proof of crystalline comparison is very similar to that of but shorter. I mean, you compute the cohomology using envelopes, I mean, log prismatic envelopes. And the log prismatic envelope is computed by the exactification I mentioned, and also the, I mean, usual prismatic envelope. And prismatic envelope and PD envelope is connected by Frobenius somehow. And using these things, you can connect log crystalline cohomology and log prismatic cohomology. I mean, log crystalline cohomology is also computed by log divided power envelopes, and that is also computed by exactification and usual PD envelopes. So yeah, the hot state comparison, by the way, so originally I proved the hot state comparison under various assumptions, but when preparing this talk, I think I found a simple approach, and now I think I can prove it in full generality, but maybe I should check all details. Yeah. And the drum comparison will be proved in full generality in the scale, the paper with Tuzi and Yao. I guess I'll stop here. Yeah, thank you.
So are there questions? So there's a question in the chat from Tong Liu to everyone. There are several questions in chat. Maybe it's best you read them yourself.
Oh, yeah. We do have finite height conditions and Niagara filtration. This will be worked out in the second paper. Yeah. But it's being written. Oh, other questions? I only see one question.
There are two questions. There's one from Tong Liu.
Yeah.
Well, actually the same question. When you know the Niagara filtration, then you know the height condition. So that will be, say, the cohomology at I has a kind of height I, right? So,
yeah.
Okay, thank you.
I see. Yes, the other question was from the earlier talk. I'm sorry. Are there any other questions?
Okay, so maybe I ask one question. So you have a comparison theorem for semi-stable scheme with integrally. So can you say something about the torsion part of relation of torsion part of eta cohomology and log crystalline cohomology?
Well, already in my paper with Cessna-Bicius, we, I guess, discuss and conclude. But by the way, existence of verification cohomology itself is kind of non-trivial and has a non-trivial consistent torsion because there is a Frobenius twist somehow in the theory. Yeah.
I see. Yeah. Thank you.
So I guess that the next activity is at 16:30. There's some sort of a gathering at Gathertown, and there's nothing until afternoon. Then, I hope I don't mislead anyone. That's my understanding. Okay, so thank everyone and thank the speakers. And this is very nice.
Yeah. Okay, I paste the information about Gathertown again, just in case. Yeah.